Hello everybody, this is Universal University coming at you with another chemistry related video. This time we're continuing on our teaching of the chemistry fundamentals by talking about one of the most important aspects that every atom has, and that is electronegativity.
True. So if you look at the periodic table, you're going to notice this pattern where the atoms that are in the top right, excluding the last line, forget about them, they tend to be really electron hogging. They're really close to completing their octet. If you don't know what that is, go watch our other video. So they really want to get some electron density around them. And what winds up happening is in large molecules, or even small molecules such as water, a dipole will form, otherwise known as like one side has an negative charge, one side has a positive charge.
Electronegativity can just be represented as how much an atom wants an electron. And it's kind of how aggressive it will be to take that electron from somebody else. Electronegativity is actually given on a very strange scale. You've got a scale from about 0.8 to about 4, just under 4. And the average atom is going to lie in that, 2 to 2.5 range, but extremely electronegative atoms, specifically fluorine, lies at 3.98. And fluorine is the most electron-hungry motherfucker out there.
Actually, it's related to reactivity in some way. If you had like the pure versions of those elements, the more electronegative they are, in general, the more likely they are to want to explode. One of the most famous electronegative atoms is obviously water. So if you look at water, like the chemical makeup of water, you'll see one oxygen molecule in the middle, and then two hydrogens in this little shape we call bent. The oxygen has 2 lone pairs, so 4 extra electrons on it, and is fairly to the top right of the periodic table. Oxygen is famously electronegative, and it likes to form dipoles. Now, in the case of water, the hydrogens are positively charged because their electron density gets pulled towards the electronegative atom that is oxygen. So what winds up happening is water is like if you had a bunch of dipole magnets, like bar magnets with a north and south pole, and you just put them into the water, they'll start to form structures. In fact, when you freeze water and turn it into ice, the structure of ice, the chemical makeup of it, which is hexagonal, is determined via the dipole interactions between the different water molecules. It's also the reason why water can dissolve stuff.
So yeah, when we're talking about having dipoles within a molecule, that's what's known as being a polar molecule. So you have 2 systems. You have polar molecules and you have non-polar molecules. A molecule is non-polar if the bonds within it have atoms of close enough electronegativity to not worry about having those extreme pulls in one direction. So for example, carbon has an electronegativity value of 2.55, while hydrogen has an electronegativity value of 2.20. So if you have a carbon-hydrogen bond, neither of the atom is significantly pulling on the electrons more. And so you'll end up with a non-polar bond, which is why you can have things like fats and oils. They have a ton of carbon-hydrogen bonds, and so there isn't that polar property.
True. So an example of this would be gasoline. So gasoline is mainly made up of these things called hydrocarbons. And hydrocarbons are just long carbon chains, sometimes cyclic, with hydrogens all on them, right? Hydro, hydrogen, carbon, carbon. If you try and mix gasoline with water, it will separate, right? Because it's energetically favorable due to interesting thermodynamic properties that the water will want to stick to itself due to the dipole interactions, and the gasoline, effectively an oil, won't. It'll actually want to form these little capsules, and then eventually it just forms its own neat layer. And that's why oil and water don't mix.
Electronegativity happens because the closer you are to the center of an atom, where all the positive, the protons live, as you get closer to that, you're going to feel the pull even greater, because as distance increases, a magnet doesn't work as strong. But when you're right next to the tip of a magnet, everything is pulling at maximum strength. And so when you have only the first valence electron shell, remember from our other video, every like 8 or a multiple of 8 electrons that you have, you build another valence shell. When you have only the first valence shell, or the second valence shell, actually, in the case of fluorine, you have maximum pull strength. And so the electrons are so close to all the positive stuff that they're pulling the nearest electron down into it to make sure that it's not like world-endingly horny for an electron.
That's one way to describe it.
Yeah, I don't really know how scientists describe all this stuff using what they call layman's terms.
Atomic world is just a bunch of magnets, and they like to interact with each other, like or positive and negative attract, positive, negative don't.
Yeah,
right,
bitch.
And
magnet.
If there's just some atoms that like to pull negative charge, and some atoms that don't. And when those two atoms mix, you get one side negative and one side positive, and then boom, it's just a bunch of magnets that are all interacting. So
that's a bunch of magnets.
Stupid magnets. I always hated them.
Yeah. So next time you are wondering why things are attracted to one another, keep in mind that on the atomic scale, there's all these little magnetic interactions going on. And this is also why you should not, under any circumstances, put sodium into water. Or put sodium, especially don't put sodium in a vial with fluorine gas. That is, you will be labeled as something very dangerous to your community.
There was this plant, they were dissolving the sodium metal in water. Their cooling system failed, and then it got hotter and hotter, and then that caused more reactions to happen until it just exploded, a runaway reaction. It looks like an atomic explosion. I kid you not.
You can't ever trust scientists, especially chemists, to do anything smart, which is why next time we're going to have to teach you guys about the demon core. Well, that does it. Well, thank you everybody so much for watching. You've been great. You've been a wonderful audience.
Beautiful, even. If you liked the video, like, subscribe, comment maybe if you really liked it. We're out. Bye.
Bye-bye.